So thanks, Renee. So this work has been done together with Maggie Billen, and I also got help from both Renee and Wolfgang. So thanks for the help. So what I'm going to talk about is well, CPO in aspect and how we are implementing it. And since it's not been merged yet and still also it may change a bit from the user point, I will actually focus the presentation mostly on the background, what you would need to know to start using CPO from a more theoretical perspective. And I will do that based on 5 questions I hope to answer. So first of all, what is CPO and why is it important? Second of all, what is it? How does it form? Then do we model this CPO? And then how is it the model being implemented in aspect? And the last question is sort of a future outlook, what remains to be improved after this. So to start out with, what is LPO/CPO and why is it important? Sort of a tricky thing because it's 2 questions in one. But and one thing you may notice already that I have here LPO/CPO, and the reason for that is that they're interchangeable. So the one stands for lattice preferred orientation, while the other stands for crystal preferred orientation, and you see that LPO is being used a little bit more in the older literature and CPO a little bit more in the newer literature, but you can use both. And what it is that crystals in a rock align in a certain direction. An example from rock here is that what you can do is you can actually visualize the direction based on the color. That's what they did here. And you see that the green color, which indicates a certain direction, is way more prevalent than the red color, which is a different direction. Way in which is more usually visualized is in these pull figures. And I don't have the time to really explain how these work, but if you would have a randomly distributed grain, if your crystals would be randomly distributed, this would all be homogeneous. You would all have, I guess, sort of a bluish color over here. But because there is a certain orientation of these grains, you can see that there are spots here where there's a high value and spots where there are low values, and they're indicated in different directions. So that's what it is. And the reason why it's important, and there are many reasons, which I also will talk about later, but for me, it's the main reason why it's important is because it will provide us for extra constraints for our geodynamic models. And it has to do with that, with seismic anisotropy. And the one thing we can constrain better is mental flow, because mental flow will cause this CPO, and the CPO influences the waves going through the grains. So these grains have a fast direction, and they will move faster to that fast direction and to other directions, and you can measure that in the surface, and that's what seismic anisotropy is. And in the large scale, how we can see this is I have here 2 maps of more or less the same region, and on the right hand side you see a GPS map, and the only thing I want you to notice here is that there's sort of a rotation going on around Idaho over here. And if you see here Idaho, you see this is the seismic anisotropy measurements, and you can see that there's actually more of a rotation around Nevada in this data set. One thing to know here is that the seismic anisotropy this fast direction is expected to be more or less, usually assumed to be more or less in the direction of the flow. And we know that's not exactly the case, and that's also why we want to do this. So to understand a little bit more what's going on, we need to ask the question, how does CPO actually form? And I want to highlight 2 processes in which they form. And one, that's actually the most important one for us, is the rotation of grains by flow in the mantle. And what I have here is a corner flow, so there's material moving up over here, and it's moving to the side over here, and here we have a top view and a side view. And there are different colors here which represent different fabrics. I will go to that in more detail now, but now just be aware that they exist. And we started in random orientation, and you see that they pretty quickly already align in this model. That's actually an aspect model. But what you also see is that they do not perfectly align with the flow, and they also go perpendicular to the flow if you look at this top model. And this has all to do with these fabrics. So what you see here is actually not just the fast directions of these grains, but already what I did here is get the elastic tensor out of it and get the fast direction of the whole tensor, which includes olivine and ancestite. The second way of forming LPO is through reprecipitation. And here's just an example of that same grain we saw before, and now heated up for a while. And the only thing I want you to notice here that here it is, you have a horizontal direction, here direction slightly changed. Okay, so now we have some idea of what it is, but how would we model something like that? And we're using or implementing the DRX algorithm. And that algorithm, what it models a rotation and of grains and crystal grains, and it models grain size change. And so the rotation is modeled by dislocation creep for normal grains, and for small grains, it models deformation by grain boundary sliding. And for the grain size, changing grain size, it models grain boundary migration, and for small grains, subgrain rotation, which are then forming these small strain-free grains. I will go to this in a little bit more detail, but this is just a high level of the processes which are modeled. And I already mentioned before that there are these different fabrics, which under different, which you saw under different conditions are prevalent, but also that they really influence how the CPO forms and what direction your fast direction of the crystal is going into. And for olivine, this can be actually very different, as we already saw. And it's very dependent on both stress and water content. And that's actually also what we've implemented. That's in addition to what the DRX algorithm normally does. And we have implemented a way that it can automatically select which, based on this graph, which type should be present and at each location. And it is actually easy to add more complex fabric selectors if you want to. Okay, so that's sort of the conceptual model we want to use. So how is it being implemented in aspects? And again, starting from a high level, we are using particles. And there are many reasons for that, which I won't go into detail now, but that's what we're using. And each particle can actually contain several minerals. It can be just olivine, just ancestite, or olivine and ancestite. And you could also implement your own minerals if you want to. And each mineral contains a certain number of grains. And then each grain contains orientation matrix or rotation matrix and a grain size, which is non-dimensional. So that's what we'll need to update in aspect in the model. We will need to update the grain size and the rotation matrix. And to get a little bit in more detail in this, I've implemented several advection schemes, the forward Euler, backward Euler, and Nicholson. But just to show you sort of high level how it works, I will show you for the forward Euler scheme, in which the new value is the old value plus the time step times the old value times a kind of derivative. And we do this both for or need to do this both for the volume fraction and for the rotation. And since the rotation is conceptually the most interesting one because it something you probably don't think too much about usually. And so here I have equal starting conditions, and here I set this derivative to 0, and here I set it that it rotates with the rotation of the particle. So the particle rotates here around, and so what you will see is this. So here the derivative is 0, and here it rotates with the particle rotation. And so what Dirac's does, the Dirac's algorithm does, is for us is just provide these derivatives. So it also makes it easy for other models to be implemented because they just need to provide these derivatives. And so to these two derivatives which are needed are, well, first rotation, and I'm showing here the spin tensor, which is the one on the right side where it rotated with the particle. And the reason I'm doing that is because this is what Dirac's algorithm model computes for this dislocation creep. And you may notice that this is actually exactly the same as this. So conceptually what happens is that you take the rotation from the particle and you modify that a little bit by deformation going on. And so if it's the grains get very small, so if they are below a certain threshold, then we actually set this whole derivative to 0 because then they deform by grain boundary sliding. For grain sizes, the change in grain size, it deforms by grain boundary migration, which is modeled by this equation, where this is the mobility. And here we have the strain energy of the particle, of the grain. Minus the strain energy of the average strain energy of all the grains of that certain mineral, of a particular mineral. And again, we have something special for small grains because these small grains are assumed to deform under a sub-grain rotation, which forms these small strain-free grains. So for these small grains, what we set the strain energy of those particular grains to 0. And what you then notice is what happens to the equation is that because we have a minus here and a minus here, the grain will actually grow. Okay, so what remains to be improved? So there are lots of things which would still need to be done at some point. One of them is to make a direct link to the seismic anisotropy from model results. So I can now compute actually the elastic tensor from the CPO based on both olivine and ancestite, and then also decompose that in different parts, but would still need to somehow have seismic rays to the model to actually know what we would observe on the surface. Also, the water, currently the water is just a field in the background. It would be nice to also add some reactions to that to make it more realistic. Other things you could think about is other models or improvements to Dirac's. Also, the figure you saw was for the fabric determination is partially populated. I don't think we actually have a better data set currently. If someone knows of one, please let me know. But we can implement better fabric determination. And also one thing which would be cool in the future and which Agnes Kirali is working on is actually coupling the CPO to the viscosity, which is also a nice further direction. Okay, so thank you for your attention.